Welcome back to a brand new explainer, Focus Learners. It is July 10th, 2026, and we are breaking down a literally massive structural shift in planetary scale AI training. If you've been following the sheer scale of modern frontier models, well, you already know we've entered a regime where the old rules simply break. Today, we're unpacking a really fascinating paper on decoupled DiLoCo and the EP architecture of resilient training. We're going to explore how AI training is moving away from rigid lockstep synchronization to something much more biological and, honestly, way more resilient. I want you to really let this thought sink in for a second. At million chip scale, failure is not an exception, it is the environment. For the longest time, our intuition was built around these clean, perfectly synchronized clusters. A single chip failing was just a rare, minor annoyance. But when you start stringing together millions of chips, wildly different hardware, unstable networks, and resources spread across regions, failure becomes a constant, everyday background reality. Someone, somewhere in that cluster, is always failing, lagging, or recovering. Always. All right, let's dive right into our system diagnostics menu for today's explainer. We'll kick things off by looking at why hardware failure is the new default at scale, and then dig into the fragility of perfect lockstep. After that, we'll introduce the availability-first approach of decoupled DiLo, see how it governs chaos through bounded disorder, and wrap it all up with the strategic implications of compute scavenging. It's a packed one, so let's get into it. Starting off with Section 1, the defaults of hardware failure, and how scale turns failure into the new normal. So at a small scale, a single GPU dying is an event. It's a problem. But at the scale of modern pre-training, coupling millions of chips basically guarantees constant global disruption. The sheer size of the operation creates this continuous friction. And that brings us to the core thesis here. Large model training is undergoing a structural shift from lockstep consistency to resilient availability. As the authors point out, training a model isn't just about accumulating flops. It's an energy system made up of chips, bandwidth, optimizer states, failure events, and governance controls. Because failure is just a normal Tuesday when the system is this huge, the architecture itself has to control how failures spread and keep the learning alive, even under really imperfect conditions. The authors frame this whole idea using what they call the energetic paradigm, or EP. And honestly, this is a brilliant way to conceptualize the problem. EP treats training like a metabolic process. It's not just mathematical equations updating parameters in a vacuum, it's a physical pathway of energy. Under this paradigm, communication bandwidth, wait times, and synchronization pauses aren't just minor technical details. They represent literal energy loss and the system's ability to actually produce intelligence. Which perfectly brings us to Section 2, the fragility of perfect lockstep, or the million-chip problem. To understand why this shift is absolutely crucial, we have to talk about the traditional pattern of AI training and why it completely buckles under the weight of extreme scale. Think about the dominant old-school approach, SBMD, or single program, multiple data. This is a consistency-first architecture. Every single accelerator has to execute coordinated steps and maintain perfectly synchronized parameters. It's literally like tying millions of runners together for a giant three-legged race. If just one single learner trips or stalls, the entire global race halts. Everyone waits. Now contrast that with the decoupled DiLoCo approach. That's an availability-first architecture. It isolates local failures so the rest of the runners can just keep on moving without skipping a beat. Let's just pause to consider how wild this reality is. In a tightly coupled, synchronized system, a local failure instantly turns into massive global energy loss. If the control boundary is the entire cluster, well, the fault domain is also the entire cluster. So a single broken chip or a tiny network hiccup isn't just an isolated issue. The rules of the system literally force millions of other perfectly healthy chips to sit completely idle. It's staggering to think that in some massive traditional runs, a huge chunk of compute time is just lost, completely wasted, just waiting on reconfigurations or stalled chips. Moving right along to Section 3, decoupled DiLoCo, availability first, and the resilient organism. So how in the world do we solve this massive bottleneck? Well, the EP diagnosis suggests that a truly resilient training system should only lose the damaged component, preserving the rest of the flow. And decoupled DiLoCo does exactly this. It achieves this massive reduction in the failure domain by splitting the system into semi-independent learners and a central syncer. So if a piece of hardware dies inside one learner, it's strictly isolated right there. It doesn't trigger some catastrophic system-wide stall. The rest of the system just keeps metabolizing data. Take a second to think about what this actually means for the industry. The real training resource is effective throughput, not nominal chip count. Seriously. If your architecture is so fragile that half your compute time evaporates while waiting for stalled chips, then bragging about having a million chip cluster is kind of misleading, right? What truly matters at the end of the day is continuous, useful learning flow. Okay, let's walk step by step through how this asynchronous pathway actually operates. First up, local compute. Each learner holds a full copy of the model and processes its own data independently. Second, compressed updates are created from that local work. Third is async transfer, where these update fragments are sent to the syncer quietly in the background. Fourth, the syncer steps in to aggregate all those available updates. And finally, step 5, the return fragments are sent back out. What's key here is how communication bandwidth is treated like a highly constrained, super precious energy pathway. By dialing down the synchronization frequency and compressing the gradients, the system drastically lowers communication costs. All right, Section 4, governing chaos, bounded disorder, and controlling inconsistency. Now, you might be wondering, and it's a fair question, if we aren't perfectly synchronized anymore, doesn't the model's quality just dissolve into pure chaos? Well, the paper answers this with the concept of bounded disorder. See, there is a massive difference between uncontrolled chaos and controlled inconsistency. Bounded disorder is this stable structure that actually allows for local variation. It means having temporary parameter differences across learners is totally fine, because the architecture repeatedly channels that variation back into a governed global learning direction. The inner optimization is happening locally, sure, but the outer synchronization is still firmly steering the ship. So how does it pull this off without totally breaking the model? It relies on some very specific, publicly detailed mechanics within the EP control layer. The central syncer uses a minimum quorum, meaning it absolutely won't update until at least K number of learners check in. It also uses adaptive grace windows, briefly waiting for a few more updates without causing idle time. Then it applies dynamic token-weighted merging to ensure everyone contributes fairly, alongside radial directional averaging to keep gradients stable. Also things like balanced tensor fragmentation, outer gradient compression, and strict learner isolation. The takeaway? Synchronization hasn't disappeared. It's just become intermittent, highly selective, and deeply failure-aware. If we view the EP enhancement map as a sort of diagnostic tool, think about the issue of bandwidth scarcity. Without this EP framing, communication is just a rigid structural bottleneck. But the EP approach treats bandwidth as an energy channel, explicitly reducing the signal load through compression and fragmentation. Or take hardware failures. Instead of letting one dead device cause a global stall, the EP enhancement shrinks the fault domain entirely to stop the failure from propagating. And this brilliantly synthesizes the core philosophy of the whole paper. Failure is not only a hardware problem, it is a control architecture problem. The energy loss isn't just the broken chip itself, it's the outdated rule forcing everyone else to stop and wait for it. By relocating control from rigid global synchronization over to resilient update governance, the training organism just keeps metabolizing compute even when pieces of it break off. Which brings us to our final part, Section 5, compute scavenging and energy recovery, and the strategic implications of all this. Up to this point, we've mostly talked technical mechanics, but the strategic and economic consequences of this are absolutely staggering. Maybe the wildest consequence detailed in the paper is compute scavenging. Because these learners can operate semi-independently, you suddenly have the ability to dynamically add temporary, scattered, or even older compute capacity to a training run without forcing a massive, incredibly expensive global pause. A brand new learner can just asynchronously pull the model state from its peers and instantly start contributing. Let the implications of that really land for a second. Heterogeneous hardware changes from a liability into a highly usable asset. In a perfect lockstep system, one older, slower chip drags the entire million-chip cluster down to its speed. But in decoupled DiLoCo, that slow chip is just another independent energy channel. Spare regional capacity, a batch of older GPUs, or compute clusters sitting idle overnight can now contribute productive training energy to a frontier model. Imperfect compute is no longer a contaminant, it's entirely recoverable energy. Grounding this back in computer science fundamentals, let's look at the CAP priority triangle. It's a classic rule stating distributed systems have to trade off between consistency, availability, and partition tolerance. At a planetary scale, prioritizing perfect, step-by-step consistency creates extreme fragility. Decoupled DiLoCo totally shifts that priority. It puts availability first, meaning training must continue, period, even when learners fail. It puts partition tolerance second, learners have to keep operating under network imperfections. And perfect consistency? That gets replaced by controlled consistency through periodic, governed aggregation. As the source text points out quite impartially, the strategic implication here is profound. Compute scavenging converts stranded flops into training energy. If frontier training can suddenly tolerate heterogeneous, distributed resources, then the architectural monopoly of having one perfectly centralized, pristine supercluster really begins to weaken. The overall supply of useful compute suddenly becomes incredibly elastic. And that brings us to a really provocative final thought for today's explainer. The future of AI clearly isn't just about building bigger clusters. It's about designing more resilient control systems over imperfect ones. So I leave you with this question to chew on. Who is actually going to win the AI race? The organization with the single largest, perfectly clean supercluster, or the organization with the most resilient architecture, capable of harvesting learning from continuous, imperfect, scattered compute all over the globe? Thank you so much for learning with me today. Keep focusing, and I'll see you in the next explainer.